Hello and welcome to this 5-minute short. And today we're going to look at heat loss from pipes. So we've got some hot fluid inside our pipe. Obviously it's going to lose some energy to the outside world now, ambient heat transfer. And we need to understand how we calculate that. And then we can think about, whether it's worth buying lagging or if we're going to do trace heating, what heat load might leave heat tracing, additional steam, whatever it might be. We can understand that heat loss and then act accordingly. So we've got a couple of sheets we're going to look at today. Where they live is under heat transfer, and then we've got pipe loss, and then we've got pipe heat loss profile. So we're going to start with just this pipe heat loss. And what this calculation does is it just takes a single point on a pipe and works out how much energy we're losing from that point. So if we look at the Capri sheet, it's filled in as always. Just to save a bit of time when you watching me fill in boxes. But again, it's the yellow boxes that we're filling in. So the first bit here, we've got this fluid condensing and non-condensing. So we're going to start off with non-condensing, and I've based this on the hot water at 100 degrees C and 10 bar gauge. So we know it's a liquid, so it's a non-condensing fluid. That's what this calculation is based on. So fluid got non-condensing, heat transfer coefficient. We can get the algorithm to calculate it, or if we know it, we can give it a value. But for a minute, let's just stick on calculated. We've put a mass flow, a nominal 10,000 kilograms an hour. We've got 100 degrees C, and I'm saying that the outside world is a balmy 15 degrees C. It's Cheshire. It doesn't get much hotter than that, even on a good day. It's probably raining as well, but we will leave it out of the calculation. We need some physical properties. So we need our heat capacity, viscosity, and thermal conductivity. And that's because we're going to calculate our heat transfer coefficients. And all we've done from that is created a PhysProps sheet on that. So you can see it's 100 degrees C. We've got water in there, and we're just picking up the values from the liquid column for that particular scenario. So we've got heat capacity, viscosity, thermal conductivity. We need to describe the pipe. So we have pipe diameter and wall thickness. And where we go for those is we've got the little pipe inner diameter tool, which will look a little bit like this. So 2-inch, shed 14, you can see there, it's got the inside diameter and the wall thickness. So if I left out the term, pressed OK, that value would then populate that cell. And you can do a quick check. The outside diameter is 60 millimeters and 60 millimeters. We're all good. For this particular example, I'm assuming there's no lagging, there's no lining, but of course, if there was, you put an inch worth of insulation, whatever it might be, a thin lining inside the pipe, you would put those in there. We then need to describe the heat transfer through those materials. So we're going to have obviously a wall. There's a pipe, so it's got a wall. So we need to give the heat transfer coefficient for that. And you can see there's lots of little red notes on here. So in the Capri sheet, we've given some typical values, some approximate values, if you're not sure to start off with. But obviously, it's better to try and get this for the particular material you're handling. But say you've got some typical values here. So I've just gone halfway on all these for the typical values. So 45 for the wall. I haven't put anything in for the lagging and the lining, but again, there are some suggested numbers in there. A little bit of dirt. So we've gone for, again, halfway through the dirt, and then a surface emittivity for a dirty pipe is 0.9 is normally a good number for that. So that's going to calculate the Reynolds, Prandtl, and Nusselt numbers, which may give you Vietnam flashbacks to university. But through the magic of science, we can use those to create an inside coefficient. And then we scroll down to the results part. And what this is telling us, with different wind speeds, so this is going 0 to 20 meters per second, we can see that the temperature profile at that point across the various, the inside wall, you've got the metal itself, you've got the lagging, the lining. So you can see how those temperatures change. Different types of heat transfer, so what's going on here. So we've got the radiation, there's natural convection, there's forced convection due to the wind. You get a total heat loss, so many watts per meter squared K, and then you've got watts per meter if you want it in. There's that kind of value. So what's humidity I'm going to lose at that particular point. And obviously, the more wind you've got, the more heat you're going to lose. So in essence, a simple-ish calculation. Now, before we go into the next bit, just to come up here again, you can, from calculated, you can go given. So that takes out these physical properties. And what you'll actually be asked to do is just provide a inside heat transfer coefficient. For non-condensing materials, there is the heat transfer coefficient calculation, and we can look at that, and we'll look at that in another video, which may help. That's calculated. The other thing you might have is you might have a condensing fluid. At that point, again, you would need to provide the inside heat transfer coefficient. The algorithms, correlations within this particular Caprice sheet isn't going to work out those condensing ones, because they're typically a factor of 10 higher than your non-condensing ones. And something we will work on within the sheet. So if you've got a condensing fluid, steam, then you can provide an inside heat transfer coefficient from some of the usual references, be it a Perry's or a Corson and Richardson. And then again, you'll get exactly the same kind of answers, or the same profile anyway. So that's from a single point. Now you may have want to know how much you're losing from a whole pipe, not just a single point on a pipe. So, and that's what this second sheet does, is heat loss profile does. So again, you'll recognize this. That's exactly the same as the sheet we just looked at. This time we've got a second column in there. So what the algorithm is going to do is, obviously, as the temperature decreases through this pipe, it needs to recalculate heat transfer coefficients. So we need to give it some data to interpolate between. So we're just giving it 2 points, and it's going to interpolate between those points. Obviously, you need to make sure that that kind of makes some sort of sense. You're not doing too big a jumps, and you might want to break the pipe up if you think, for some reason these aren't straight lines, and you could model that in FizzPack just to check it makes sense to just look at 2 points. And of course, once you get to the final temperature on your pipe, you want to make sure that that point is less than that. You want the algorithm doing that interpolation to be interpolating, not extrapolating beyond, either 100 or below 50. So you might need to go back depending on what temperatures you get to at the end. These are all the same as we've seen before. And again, we've chosen calculated here. We could then go for given or calculate. We've gone calculated here. This is all the same as before. This is all the same as before. But what we've got now is something a little bit different. So this is giving our pipe profile. So in this case, I've got a 50-meter pipe. We've chosen a wind speed, in this case 20 meters per second. And then you can see we've got this nice table of data. You can see the temperature is decreasing. So it goes from 100 degrees C down to 98.3 degrees C. You can see those heat transfer coefficients, how that's broken up as before. You've got your heat loss rates decreasing as it goes along the pipe, so the temperature's dropping a little bit. And then we've got the total heat loss, so that's going to increase as we go along the pipe. So in all, we've lost 20 kilowatts across the length of that pipe. So this is probably a more useful sort of value if you are thinking about how much energy do I need to input if I need to counteract the losses due to the ambient heat transfer. Wind speed up here, 20 meters per second. When I was thinking about this, I'm not really sure what 20 meters per second means. And I did have a little look on the internet. So 100 miles an hour is 44 meters per second. So that's about a 50 mile an hour wind. That's pretty blowy. But you might want to change that and have something that makes it a bit more intuitive. So we could put miles per hour in there. And now we've got 20 miles per hour. We can go back to 50, get somewhere close to where we were before. So you can change this value, this unit here, to make your wind speed a little bit more sensible or more intuitive is a better way. So maybe 10 miles an hour is a more likely wind speed you want to model, and it gives you that loss. So that's as far as we want to go for this particular 5-minute short. We'll then look at something like FlowNet and Piper down the line to see what we do with these and how they will influence various models. Thank you very much.